Friends, good morning. We were dealing with and discussed about carbenes. Carbenes, as we know, they are electron deficient species and also neutral in nature. Whereas carbocations are electron deficient carbon species with positive charge on it. Carbenes can exist in both singlet state and triplet state. If it is in singlet state, it will be in sp2 hybrid form, and in triplet state, the carbon will be in sp hybrid form. And now, today's subject of discussion is preparation of or generation of carbenes. The carbenes can be generated by first approach, which is called as isopolar approach. The photolysis or pyrolysis or transition metal ion catalysis of various organic compounds. The lysis by using the light is photolysis. The breakage by using heat energy is pyrolysis. And instead of photolysis and pyrolysis, we can also use transition metal ions as catalysts. And this come under the category of transition metal ion catalysis. By using transition metals as catalysts, we can carry out the production of carbenes. We can decompose diazoalkanes by using copper salt or by using transition metals. I take dichlororuthenium tris triphenyl phosphine and treat with diazoalkane like diazomethane. Diazomethane we know here CH2 minus N triple bond N plus. It reacts together to give rise to a carbene complexed with the transition metal along with the liberation of nitrogen. The alkyl, aryl, and acyl substituted carbenes can be prepared from diazo compounds. And the second method in this is pyrolysis or ketolysis of ketenes. Now, ketenes should be prepared first. If I take an acid chloride in which the alpha carbon has a hydrogen and treat with a base like sodium hydroxide, this carbon is acidic enough to donate a proton, and sodium hydroxide ions are basic enough to obstruct that proton. OH minus abstract the proton, hydrogen as H plus. When this H moves as H plus, as OH already has excess electrons, the electrons are left onto the carbon. Once the electrons are left onto the carbon, it gives rise to corresponding carbene ion. The carbene ion which is formed, it forms bond with the adjacent carbonyl carbon, owing to the positivity of this carbonyl carbon to maintain its stability. But with this excess bonding on this carbonyl carbon, which is already tetravalent, it becomes pentavalent. We know that carbon is tetravalent. If it is having more than that, it becomes unstable as it cannot maintain its valency. Thus, it kicks off chlorine. Once it clicks off this chlorine, the chlorine which is kicked off as Cl minus, the Cl minus will combine with sodium plus and it loses sodium chloride and it gives rise to a ketene. Ketone means RCOR. Here, it is a ketene means it has ketonic group and ene group. That's why it is called as ketene. If I heat this ketene, the lone pair of electrons on this oxygen forms bond with the adjacent carbon. The carbon has to maintain its tetravalency. That's why pi electrons moves on to the next carbon, giving rise to carbene ion. Then it is unstable, and this has formed already one bond over here. It has become C triple bond O, and as it is flanked with oxygen and electronegative atom, this carbon is positive, and the pi electron, this electrons are moved over here, and the C bond is over here. This is more positive center. To satisfy this positive center, this electrons moves onto the oxygen and this carbon. Once the electrons have entered into, another time the electrons are went out, both has become equal. And this loses as carbon monoxide, and it gives rise to a carbene. Carbene is neutral because of the fact that once the bond breakage occurs with incoming of electrons, here pi electrons moved onto the carbon. Next time the carbon-carbon sigma bond got broken and these electrons are moved out. Once it comes in, it is carbene ions. Once it goes out, it becomes carbene. Carbenes are neutral because once the electrons have come inside and another set of electrons has went outside. That set has become neutral. It's a neutral carbon. This is how the pyrolysis of ketenes can give rise to corresponding carbenes. Not only the pyrolysis of carbenes of these ketenes, it can also, this lysis can be carried out by using UV light. Instead of heating, if I use UV light, also this dissociation occurs, ketene dissociation occurs, and it gives rise to carbene along with the loss of carbon monoxide. Diazirenes, if I take and oxidize it, it removes its hydrogen and gives diazirine. This diazirine can undergo dissociation in the similar fashion. The carbon nitrogen bond breaks and these electrons moves over here. It becomes N triple bond N. The nitrogen has to maintain its tetravalency. That's why this has become positive center, and this carbon nitrogen bond breaks and carbon electrons moves towards carbon. These electrons moves towards nitrogen and these electrons from nitrogen moves towards carbon. The electron out and electron in has taken place to give rise to a carbene with the loss of nitrogen. Similarly, epoxides, if I treat alkene with peracids, I'll get corresponding epoxide. And when I heat this, or if I pass UV light through this, this bond breakage occurs to give rise to a carbene and a carbonyl compound. The carbon oxygen bond breaks, this electrons moves towards carbon minus, and it is unstable. That's why these electrons move, the bond between carbon carbon breaks, these electrons moves towards carbon, and it has to this becomes carbene ion, and to maintain this electron tetravalency, the carbon oxygen on breaks and this electrons moves towards this carbonyl carbon, and it gives a carbonyl compound and an carbene. This is the isopolar approach. Photolysis or pyrolysis of ketenes, diazirines or epoxides can give rise to generation of carbenes as reaction intermediates. Another method of approach is polar approach. This is called as alpha elimination. That is 1, 1 elimination. Elimination takes place from a single carbon. This is called as polar approach. When I take an alkyl halide and treat with a base, I'll get a carbene and an hydrogen halide. For this, we use a strong base like alkyl lithium, tertiary butoxides, or any alkoxides, or lithium diisopropyl amide. The strong bases like this are used. If the carbon in this is acidic enough to lose a proton, is more acidic, then a weaker bases like sodium hydroxide can be used. CHCl3, when I treat with a base Na plus OH minus, this carbon hydrogen bond is weak because of the fact that it is flanked with three electron withdrawing groups, which withdraws the electrons from the carbon and renders this carbon electron deficient. With less amount of electrons, it is holding the hydrogen. That's why the bond is weaker. The as it is weaker, it is acidic enough to donate a proton. OH minus, I take as to base. If I abstract the proton from this, once it abstracts the proton, the carbon hydrogen bond breaks and electrons moves onto carbon. It gives rise to CCl3, sodium salt, and CCl3 minus. A carbene ion is generated. Then chlorine moves along with its electron pair, giving rise to dichlorocarbene and a chloride anion. This is 1,1 elimination. Hydrogen and halogen has been removed from the same carbon. That's it is called as 1,1 elimination. Now we can see a few examples here. Instead of using sodium hydroxide, if I have a dihalide compound and treat with lithium methane or methyl lithium in tetrahydrofuran, it loses bromide as out as methyl bromide, and lithium combines with this Cl to give an intermediate. This lithium combines with chloride, takes away as lithium chloride and gives rise to carbene. This 1,1 elimination can occur provided that this R group do not have hydrogens on it. If there are hydrogen on this beta carbon, then beta elimination or E2 elimination predominates and this reaction fails. This is the limitation of this approach. That's why we go for non-polar approach. Another approach for production of carbenes is decarboxylation of trihaloacetates in solvents which are aprotic in nature, like dimethyl sulfoxide, dimethyl formamide, etc. If I take metals, so the salt of trichloroacetate and heat in aprotic solvent, it loses carbon dioxide to give rise to carbene ion. Then the carbon chlorine bond breaks, the chlorine moves out with electron pair and combines with M plus and gives rise to corresponding MCl, giving rise to a dichlorocarbene. This is the third approach of generation of carbene. Thermolysis or pyrolysis of trihalomethyl mercury compounds can give rise to carbenes. Trihalomethyl mercury compound. If I heat it strongly at 80 degrees centigrade, It loses phenyl mercuric bromide, giving rise to dichlorocarbene. Carbenes can be obtained from carbonyl compounds. This is the fourth approach. Aldehydes and ketones can be converted into paratoluene sulfyl hydrogens or tosyl hydrogens. How can we do this? We take an aldehyde or a ketone and treat with tosyl hydrogen. These two reacts together, loses water molecule and forms an hydrazone or R-C double bond N NHSO2 C6H5CH3. The tosyl hydrazone, when I treat with sodium methoxide Na plus OMe minus, OMne minus abstract a proton from here, it becomes N minus, and this combines with metal methyl and forms a metal salt off or sodium salt off the corresponding hydrazone. This hydrazone, it loses metal minus this lone pair of electrons for air moves, and this phenyl sulfonyl group gets kicked off, and it gives rise to corresponding diazo compound. The diazo compound which is formed can be heated. It loses the electrons, dissociate over here, and gives rise to a carbene with the liberation of nitrogen. These are the 4 to 5 methods of preparation of carbenes. Let us look into the reactions of carbenes in the coming class. Till then, have a nice day. Thank you.